The most expensive mistake in home energy can happen before a single panel is installed. People often begin with hardware, solar panels, a battery, an inverter, maybe a generator connection. But hardware is not the system. A backyard power plant is really a chain of decisions about what must keep working, what can stop, how long the property should operate without the grid, and what happens when sunlight, fuel, weather, or household demand does not cooperate. Depending on the design, a home can have solar generation and still have little or no useful backup during a blackout. It can also have a large battery and waste most of its stored energy on loads that were never critical. That creates the first question in this file. What is the minimum system that keeps the important parts of a home operating without paying to support everything at once? The answer is not hidden in a panel catalog. It starts somewhere less exciting, with the load list. And one detail on that list changes the entire design. Before we get there, this investigation will separate four things that are often blended together: generating electricity, storing it, reducing demand, and controlling what receives power when the grid fails. If you want more dark survival files like this, subscribe, leave a like so this reaches more people, and comment which preparedness system should be investigated next. It will also show why a system that looks smaller on paper can sometimes be more useful in a real outage, why monthly electricity use can hide the loads that matter most, and why the phrase "pays for itself" needs to be examined carefully instead of repeated as a promise. The first piece of evidence is the simplest one. A power system does not fail only when it runs out of electricity. It can fail when demand arrives at the wrong moment. That opens the second question. Why do homeowners sometimes size a backup system around normal consumption, then discover that it cannot support the one appliance they considered essential? The problem begins with the difference between energy and power. Energy is how much electricity a load uses over time. Power is how much it demands at a given moment. A battery can hold enough energy for several hours of modest use and still be paired with an inverter that cannot comfortably handle a large starting surge. A property can also have enough solar capacity to produce useful energy across a day, but still be unable to run every heavy load simultaneously. The practical decision is therefore not how many panels do I need. It is which loads must run for how long and which of them create the highest instantaneous demand. Here's what the data actually shows when you use your own household measurements instead of a generic average. The answer changes from property to property. A refrigerator cycles, a freezer cycles. Lights may use little compared with heating equipment. A water pump may run briefly, but demand much more power at startup than small electronics. Electric resistance heating, large air conditioning systems, electric water heating, cooking appliances, workshop tools, and pumps can dominate a backup plan even when they are not running all day. Without a supplied case file, there is no honest universal number for the right battery or solar array. The useful method is to build a private case file for the house itself. Start with the loads that protect food, water, communication, basic lighting, medical or accessibility needs where relevant, and any property-specific equipment that cannot safely be ignored. Then separate them into three groups: must run, can run occasionally, and can stay off during an outage. That single act can reduce confusion before money is spent. It also exposes the first contradiction. People often describe resilience as adding more capacity, but resilience can begin by deliberately planning to use less. Every watt that does not need to be supplied is a watt the generation and storage system does not have to chase. This is where efficiency stops being a lifestyle slogan and becomes part of the power plant. Better insulation, efficient refrigeration, LED lighting, smart scheduling, shading, ventilation, and deliberate appliance choices can lower the size of the backup problem. Not every upgrade will be economical for every property, and no saving should be assumed without local measurements. But the design logic is clear. Reducing critical demand can make the same storage last longer, and can make limited generation more useful. The next layer is generation. Solar is useful because its fuel does not depend on delivery, but output is variable. Production changes with time of day, weather, season, shading, orientation, and equipment conditions. Nameplate capacity is therefore not guaranteed usable energy at the exact hour a household needs it. A resilient design treats generation as an input that must be managed. The missing layer in many simple diagrams is control. The inverter and backup equipment have to manage how power is converted, stored, and delivered, while selected circuits may need to be isolated from ordinary household loads. Monitoring should show what the system is producing, storing, and consuming. A grid-connected solar installation designed to reduce purchased electricity is not automatically the same as a backup-capable system. The exact behavior depends on equipment and configuration. That distinction should be verified before purchase, not after a blackout. But knowing the rule is not enough. You need to know when the rule fails. A homeowner can identify critical loads, buy storage, and add solar, yet still create a weak plan by assuming ideal weather, ignoring operating limits, or allowing several high-demand loads to start together. The system can also fail through behavior. If a household does not know which circuits are backed, people may use the reserve as if the grid were still present. So the equipment needs an operating plan. Which loads stop first? Which can be scheduled when solar production is strong? What reserve should be protected for overnight use or an uncertain next day? Who knows how the system changes modes? These questions keep an expensive installation from becoming decorative during the event it was meant to handle. This opens the third loop. Why can a smaller system, deliberately limited, sometimes protect a home better than a larger system that tries to preserve normal life without priorities? Batteries do not create energy, they move it from one moment to another. A reserve protected for refrigeration, communication, water, and basic lighting can be more useful than a larger reserve repeatedly spent on non-essential loads. The goal is not to recreate the grid in miniature at any price. It is to preserve the functions that matter most with a system the property can support, maintain, and understand.
Preparation is not only about surviving a crisis, it is about building systems that help you become more resilient before that crisis happens. The Self-Sufficient Backyard is a practical guide for food production, water, preservation, energy solutions, and off-grid projects for small properties. If you want to explore these systems, use the link in the description or the pinned comment. Now, back to the file.
This brings us back to where we started. What is the minimum system that keeps the important parts of a home operating without paying to support everything at once? The answer is not a universal battery size or a universal panel count. It is a critical load plan built from the property's own measurements, followed by enough compatible generation, storage, conversion capacity, and control to serve those loads for the chosen outage scenario. The design begins with decisions, not equipment. First, identify what must keep working. Then measure or estimate its daily energy use and its highest likely simultaneous power demand. Then decide how long the system should support those loads without dependable grid power. Only after that does it make sense to evaluate the hardware. That closes the first loop. But it reveals a more important point. The cheapest kilowatt hour in a backup system may be the one you never need to produce, store, or convert. Energy efficiency and load management are not side topics, they are capacity. If a refrigerator, lighting plan, ventilation strategy, or water system can perform the same essential job with less electricity, the entire backup chain has less work to do. This is also where smart planning can outperform blind expansion. Rather than trying to run a home exactly as it runs on the grid, a resilience plan can create operating modes. Normal mode is ordinary life. Conservation mode begins when the grid is unstable or an outage is expected to continue. Critical mode reserves power for the small set of loads that protect food, water, communication, safety, and property-specific needs. The names do not matter, the hierarchy does. A system with priorities can degrade gracefully. A system with no priorities tends to discover its limits all at once. The next question is money, because the title becomes misleading if pays for itself is treated as a guarantee. A household may recover part or all of an investment through reduced electricity purchases, local compensation rules, incentives, avoided outage losses, or long service life. In another location, different tariffs, equipment prices, financing, maintenance, sunlight, or regulations can change the result completely. Without a location-specific model and current local rules, there is no honest payback period to claim. So split the phrase into two tests. The financial test asks what the system costs over its life compared with what it realistically saves or avoids. The functional test asks what the property keeps doing when outside power is unavailable. Those are not the same result. A serious calculation needs real bills, local rates, equipment quotations, maintenance assumptions, current rules, and the household's actual consumption pattern. None of those inputs should be invented. The next layer is battery strategy. Storage is often treated as one capacity number, but usable backup also depends on the battery system, operating range, inverter limits, temperature, age, control settings, and the connected loads. The practical question is not only how large is the battery, but how much stored energy is available for the plan and how quickly can the system deliver it. Peak power and duration must be considered together. Solar has the same planning problem. More panels can create more production opportunity, but that energy must be used, stored, exported where rules allow, or curtailed. The configuration matters more than the slogan. Then comes maintenance. Batteries, inverters, connections, breakers, transfer equipment, mounting, ventilation, weather protection, and monitoring all need appropriate inspection and service. A resilient system should be understandable enough that the household can recognize abnormal behavior. Documentation, labels, shutdown procedures, and qualified service contacts matter. Any equipment connected to household wiring or the utility should follow applicable electrical, building, and professional requirements. This is infrastructure, not a collection of survival gadgets. Now consider a representative case, not a documented event. A family wants backup power because short outages have become disruptive. Their first instinct is to preserve normal life: cooling, cooking, hot water, refrigeration, entertainment, every outlet, every room. The proposed system becomes large and expensive immediately. Instead, they create a critical load list. Refrigeration stays, a few lights stay, internet and phone charging when the network is available. The water system stays because the property depends on an electric pump. Heavy heating loads, electric water heating, discretionary workshop equipment, and other non-essential circuits are removed from the first backup tier. The design suddenly has a different shape. But then the second loop problem appears. The family only looks at total daily energy and misses the pump's starting demand. On paper, the battery seems adequate. In operation, the power electronics must also handle the momentary demand when that motor starts. The correction is not simply buy the biggest battery. It is to size and configure the inverter, storage, circuit priorities, and starting behavior around the actual load profile. That is why homeowners sometimes size a system around normal consumption and still fail to support the appliance they care about most. Monthly energy totals can hide short, high-power events. That closes the second loop. The family then writes a three-stage outage plan. During daylight, flexible loads are scheduled when solar production is available. After sunset, the house moves into conservation mode. If stored energy falls toward the reserve they chose to protect, only the highest priority circuits remain. Nobody has to improvise under stress because the decisions were made before the outage. The system is smaller than the fantasy version that tried to run everything, but its purpose is clearer. That closes the third loop. A deliberately limited system can protect a home better because it controls demand, preserves reserves, and makes failure modes visible before capacity is exhausted. More hardware without priorities can simply create a larger pool of energy to waste. The ancient record goes silent here, but the lesson remains. Resilience is measured by how normal a house looks during the first hour without the grid. It is measured by how long the important functions remain available as uncertainty grows. That changes the design question one last time. Instead of asking how to build a house that never notices an outage, ask how to build a house that knows exactly what to do when one begins. Generation provides options. Storage moves those options through time. Efficiency stretches them. Controls protect them. Planning decides what they are for.
Put those layers together and the idea of a backyard power plant becomes less dramatic and more useful. It may include rooftop or ground-mounted solar, battery storage, a critical loads panel, efficient appliances, manual or automatic controls, and a written operating plan. It may be larger or smaller depending on the property. It may reduce purchased electricity, provide backup capability, or do both. But none of those outcomes should be assumed from a product label. They have to be designed, measured, and verified. The central lesson is simple. Energy independence is not the absence of the grid, it is the presence of choices when the grid is no longer a choice. The strongest backyard power plant is not the one with the most impressive equipment. It is the one whose limits were understood before the lights went out.